thermal images to show our product in quite literally a different light.
This is a photo of the thermal pad immediately after turn-on. You can see that clearly the wire is a lot hotter than its surroundings.
This image depicts 30 seconds on, and you can clearly see that the heat is dissipated evenly over the surface of the heat pad. This is due to our reflective aluminum shielding and the heat dissipation that happens in the low-density fan.
The final picture demonstrates the heat burst taken from behind, and if you compare the colour of these heat pads with the thermal pads, you can see that the aluminium shielding is effectively working from preventing heat dust escaping through the backs of the pads and focusing on the target area underneath instead.
We hope that these products will benefit those suffering from pain from heat shock, circuit electric shock, or just a comfortable and thrifty way to stay warm during colder times. Unfortunately, unlike today, Matthew, sweating away. I'll now pass you over to James, who's going to do the technical bit.
Thanks very much. Okay, well, my work over the past few months was developing this inner heat technology that we use in our heat pads. So what does that consist of? Well, firstly, we need to determine the equation that describes the wire temperature as a function of time, easy enough. Once this equation has been established, it is then just a matter of finding physical reasons for the constants that appear in it in order to use it to predict it. After that, it is important to check it against experimental data to make sure it agrees with observations. Finally, modelling the heat equation was essential in order to investigate the effect of heated wire has on its nearby environment to so keep the product safe. So let me now move on to discuss how the equation for the wire temperature was calculated. Preliminary tests on the heat-resistant wire imply that the rising temperature was proportional to an exponential decay with time. So if we assume that is the case, and that any arbitrary constants I put in are independent of the variables, then we arrive at this very simple relationship here, with lambda and omega, the constants that define the whole equation. So the equation's limits are important here. You see that it is, as you would expect when you heat something up, as time goes large times, the case temperature tends to this value omega. Okay, so here, this is a little video to show you what's going on. So the blue is cold, obviously red is hot, and just the rate of change of this colour depends only on the lambda in the equation here. Okay, so that's all well and good. So does the theory hold up to experiments? Well, first of all, you need to determine what the constants are in the equation. So here you have a power relationship between temperature, area, that sort of thing. And you can see that actually most of these things are dependent on the type of wire we bought. The only thing we really have control over is the A, which are the surface areas, which is controlled just by increasing or decreasing the length. Lambda you can find by discussing the energy equation. And so you put in your equations, you put your theory, and here is what the red line shows, and the blue line is actually a real vector joined together like that. So you can see that there's excellence, much better than I expected, the agreement between the two curves, and so we were confident that this equation was useful to model our heat product. Alright, so firstly, we need to solve the heat equation, and that's what it looks like. If you assume a steady state solution, it becomes much easier to solve. It becomes the flattest equation. And so the method that I used to tackle this in order to solve it was called the UCL method. And that essentially works just by assuming space is a continuous, it's made up of small squares like this. Then all you have to do is apply your boundary conditions to your equation, propagate through time until the new temperature equilibrium has been established. So here's a video of that happening here. These three spikes here are now the inductive wires held at a constant temperature, and you let it propagate through time. And you see that the temperature rises almost to meet the wire temperature, but importantly not to the wire temperature. This is the point. Although the qualitative argument quantitative argument that everything evens out to this sort of lower temperature is the basis of the model and is the importance of it. So after that, I'll now pass over to Messrs. Zacharias and Rashid, who will talk about the third and final product from which we're going to Thank you.
As George has mentioned already, lower back pain is the most common form of pain that people experience. So we at UCL explored a new way to combat this problem. The prestige massage wrap is a convenient and effective way to remove pain.
For the operation of massage bed, an interface calculator was used for controlling this device with a laptop. A national instrument for this purpose, a national instrument USB was used, which is compatible with laptops. It was used also an 8 Darlington transistor, consists of 8 transistor pairs and 8 diode tabs for conducting the current in only one direction. This is shown in this circuit diagram. 8 Darlington transistor is essential because it's connected with a 6-volt battery supply and is used to amplify and provide adequate current to the 4 motors for a suitable vibration effect. Each of the motors rotates an eccentric mass so as to cause its base to vibrate. Therefore, each motor provides an independent massaging effect. The lab is used for controlling the motors with different modes. A symbol code was written so as to enable the user to control motors in pairs and change the time between class operations.
As Maras has already mentioned, the wrap has 4 motors in the back spinning off-axis weights in order to produce massaging effects when activated by the control program. The motors are deployed inside semicircular plastic casings to increase the surface area of vibration on the back, and also to allow the motors to spin when under pressure from the wrap. The circuit we made was, the circuit that we used was made using strip board, which is a common material in electrical prototyping, to allow us to easily modify our circuit because we assumed, given the prototype, we have to change something at some point, and enable us to solder the components onto it without having to etch a custom PCB. Arrowlight glue was then used to glue the motors into the belt because it provided a very strong hold between the neoprene and the aluminium motor casing. Here you can see a few pictures of the construction of the silicate being soldered in the top right and the top left and the bottom, it being fitted into the casing. We then conducted a survey to see how effective the massage belt would be, and people gave it an average of 4 out of 5 stars in terms of how much the massage it provided. Those that tried our products who were already suffering from back pain said it provided at least a moderate decrease in their symptoms, with some saying that it helped them quite a lot. The optimal program settings were also discovered during the course of the survey, which was having 1 motor on each side of the spine active at any one time, with a 5-second delay. After which the first 2 motors are turned off and the second 2 are turned on. This produces waves. The motor vibrations from this produce waves, which give the illusion of it being massaged first in one direction and then the other. In this video, you can clearly see these waves we can clearly see these waves at work. Well, for clarity's sake, all the motors are on and then all the motors are off at any one time, so that the waves generated can be seen more clearly. As this is an initial prototype, a final product would also include a mobile user interface, so that it can be controlled not from a laptop, from a mobile phone, or an iPad, or a mobile device. We've also run more extensive studies to determine the effects of the massage belt and see in which ways the device could be improved. I'll hand over to James for some concluding remarks.
Thank you very much. So, what have we learned over the course of the last few months? So, the first conclusion we came to was that we realised pain is very subjective, and so it's unrealistic to claim that our product can tackle a whole range of pain. However, what we have shown is that they can help relieve pain in certain situations in both areas. Secondly, we see a very positive response to all of our products so far, and so we should work to implement any changes that these happy customers implement. Thirdly, and most importantly, it was a very interesting and fun experience for us all, meaning we had a better work ethos and better quality final product. Okay, so now on to a few developments we want to make. In the near future, our first intent is to engineer a smartphone application. We see that this will make our product easier to control and appeal more to modern-day users. We also aim to make a user-friendly interface for the rack. We believe that this will make our product easier to control, and it will be simpler and more intuitive to use for customers. Right. Finally, our biggest and most exciting ambition is to integrate the inner heat products with the rack in order to create a fully controllable, almost whole upper body pain relief suite, resulting in great customer satisfaction. Okay, so now we'd just like to finish off with a few acknowledgements. So,
without Mr. Bernard Bristol's help up in the top there, we've never been able to do it. Technical expertise has been sublime, and he's got a screw project really. And Mr. Mark Sterling likewise on the lab team provided lots of tools and things for us to use.
and thirdly, Professor Harker, for your notes on Gauss theory from last year. Thank you very much for that. And finally, but certainly not least, thank you to our board member, Dr. Martin Fry. We will take, if you want to try a product, please come down, please try them. Thank you.
Have there been any double-blind placebo-controlled studies that show that there is benefit of heat therapy or massage?
I think Mary, this is your section.
We personally didn't undertake any of those tests, but we checked to make sure that both of the techniques that we were comparing to one data set, there was a astounding difference between the two in both cases for heat and pain.
Have you registered the name UCL clinic?
Yeah. Clinic. Your product works now, but what is the cost of the product being made yourself, and what's the price in the market you will sell it, and what's the net profit in that?
We did do a bit of introductory market research into that area, and we found that people were most likely to pay between £20 and £30 for a massage bill. For the heat vest, we haven't yet done that, but it's something we hope to do in very near future.
Developing these products is a bit higher because obviously we have to buy things not in mass orders, so pretty much on the budget.
Questions?
They want to try our products still.
You want some massage?